Good morning. In today's session, we will take down a problem based on torque on a current loop, which is placed in a magnetic field. Now take down this question. A circular coil of 30 turns, circular coil of 30 turns, a circular coil of 30 turns and radius 8 centimeter, carrying a current of 6 ampere, is suspended vertically in a uniform horizontal magnetic field of magnitude 1 Tesla. The field lines make an angle of 60 degree with the normal of the coil. Calculate the magnitude of the counter torque that must be applied to prevent the coil from turning. Next, would your answer change if the above circular coil were replaced by a planar coil of some irregular shape that encloses the same area. Bracket you write all other particulars are also unaltered. All other quantities are also unaltered. That completes the question. Now we will read and we will list out the given things. Any sum given, first list out the given things. Now read this. A circular coil of 30 turns. Therefore number of turns we know. That is N is 30. And radius 8 centimeter, carrying a current of 6 ampere. Radius R is 8 centimeter. And then what else is given? Current. (6 ampere) is suspended vertically in a uniform horizontal magnetic field of magnitude 1 Tesla. Now magnetic field has a magnitude of 1 Tesla. The field lines make an angle of 60 degree here I'll write 60 degree field lines make an angle of 60 degree with the normal of the coil. Therefore theta is 60. Theta is 60 degree. Calculate the magnitude of the counter torque that must be applied to prevent the coil from turning. Now we know that when a rectangular coil or any shape coil is placed in a magnetic field, the coil experiences a torque, and we know how to calculate the magnitude of the torque, and because of this torque the coil tries to turn. So this is basically a twisting torque. Now the counter torque which we are applying must be equal in magnitude of the torque which the coil experiences. Therefore if we find the torque on the coil, it means that we have to apply a counter torque with the same magnitude. Now here the given coil is circular. Let me draw a diagram for this. The given coil is a circular coil and it is freely suspended. Freely suspended in a magnetic field. The coil is freely suspended in a magnetic field, and it is given that the current in a coil is 8 centimeter and it has so many number of turns also. Now the area vector and the direction, the magnetic field makes an angle 60 degree with the normal to the plane of the coil. Therefore if the normal to the plane of the coil is in this direction, now our magnetic field will be making an angle 60. We can write this is B, which B, and then this is area vector A because that is perpendicular to the plane A, and then this is B and E, and they make an angle 60 degree which is given. Now we will calculate first what is the torque. According to the equation, we have torque on the coil as given by torque acting on the coil, which is equal to NIBA sin theta. Now substitute all the values. Number of turns in the coil is 30, current is 60, B is 1 Tesla. Now what is the area of the coil? It's a circular coil and the radius is 8 centimeter. So area will be pi r square. Pi r square. So it is pi into r square. R is 8. Centimeter you convert it into meter. Pi r square. Pi r square. 8 multiplied by 10 to the power minus 2 and its square, multiplied by sin theta, sin 60. Sin 60. So now calculate this. Do the calculation. Sin 60. Now if you do the calculation, you are going to get the value of torque. 30 multiplied by 60 multiplied by pi into r square, that is 8 multiplied by 10 to the power minus 2 whole square. Why 10 to the power minus 2? Because we are converting centimeter to meter into sin 60. So torque, if you do the calculation, it comes to around 3.13 Newton meter. Now we need to apply a counter torque which is of the magnitude to prevent the coil from turning. Therefore, magnitude of the torque, magnitude of the counter clock required, magnitude of the counter clock required to prevent the coil from turning. Prevent the coil from turning is equal to 3.13 Newton meter. Newton meter. This much Newton meter. .13 Newton meter. Now next is we have another question. First we'll read that. Would your answer change if the above circular coil were replaced by a planar coil of some irregular shape that encloses the same area? All other quantities are also unaltered. Now see, in this case the torque is given by NIBA sin theta. Now you are replacing this circular coil by another coil of irregular shape but maintaining the area same. Planar coil of some irregular shape that encloses the same area. So this is important here, that encloses the same area. So if the area remains same and also all the other quantities are also unaltered. If area is same, if all other quantities are unaltered, then your torque is not going to change. Therefore, you will be the answer won't be changing if we have an irregular shape but maintaining the same area. As long as the area of the planar coil, as long as the area of the planar coil remains same, the torque on the coil also remains same. The torque on the coil also remains same. So our answer will not change as long as the area of the coil and also the other quantities remains same. Hope you understood this problem.